In section 4.6, we're going to talk about modeling with exponential and logarithmic functions. This section is particularly long, so I'm going to break it up into two parts. The first thing we're going to talk about is a particular type of exponential growth called doubling time. A model for the doubling time is n of t is equal to n naught times 2 raised to the t over a, where n naught is your initial population, a is going to be the doubling time, and t and a, because they're both units of time, need to be in the same units of measurement. So in problem 1, under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in a colony. Find a model for the bacteria population after t hours. Remember that the phrase find a model is code for write the equation. So the equation is going to be n of t equals n naught is going to be 1,000 because that's our initial population, times 2 raised to the, well, the doubling time is 3 hours, so 3 goes in the denominator. That's our a. And we don't know what t is, so there's our equation. Now we're going to use that equation in part B in order to solve how many bacteria are in the colony after 15 hours. So we're going to plug in 15 for t. So n of t is equal to 1,000 times 2 raised to the 15 over 3, which is going to be 32,000. And then in part C, we want to find out how long it will take for the bacteria count to reach 100,000. That means we're going to make 100,000 equal to 1,000 times 2 raised to the t over 3. Because this is an exponential equation, we're going to rewrite it in log form, but in order to do that, we first must isolate the exponential part. So we need to divide by 1,000. So 100,000 divided by 1,000 is 100. In log form, this is going to be log base 2 of 100 is equal to t over 3. So you can use log base in your calculator or the base change formula in order to evaluate the log of 100 divided by 2. Whatever you get when you do the log base 2 of 100, whether you do log of 100 divided by log of 2 or you use log base in your calculator, the last step is going to be to multiply that answer by 3. So you should get approximately 19.93, and the unit of measurement was hours. So you can say 19.93 or about 20 hours. In example 2, a certain breed of rabbit was introduced onto a small island 8 months ago. The current rabbit population on the island is estimated to be 4,100 and doubling every 3 months. What was the initial size of the rabbit population? So remember they said that they introduced the rabbits 8 months ago, but they didn't tell us how many they introduced 8 months ago. They just told us that the estimated population rate now is 4,100. So we're going to do 4,100 is equal to n naught times 2 raised to the 8 over 3. 3 is the doubling time. That goes in the denominator of the exponent, and the t for time is going to be 8 months. Remember that t and a need to be in the same units of measurement, but luckily they're both in months. So all you really have to do is divide 4,100 by 2 raised to the 8/3. Since this is a population, you need to round it to the nearest integer, and you should get approximately 645 rabbits. Estimate the population 1 year after the rabbits were introduced to the island. Well, now I know the initial population. Remember that t and a have to be in the same units of measurement. Since the doubling time is 3 months, but we want to find the population 1 year from now, we have to plug in 12 for t, not 1, 12. And then you just plug in your calculator 645 times 2 raised to the 12 over 3, and you should get approximately 10,320 rabbits. Another type of exponential growth that's not necessarily doubling is called the relative growth rate. We use the equation whose base is e, and we've actually seen a whole bunch of these equations throughout the unit. They've just given us the equation in this form. N of t is equal to n naught e raised to the rt. N naught's your initial population, r is your relative rate of growth, and t will be your time that needs to be in the same units as your relative rate of growth. So in problem 3, the initial bacterium count in a culture is 500. A biologist later makes a sample count of bacteria in the culture and finds that the relative rate of growth is 40% per hour. Find a function that models the number of bacteria after t hours. Well, it's going to be n of t is equal to 500 e to the 0.40 t. Remember, you got to change 40% into decimal form. So in part B, what is the estimated count after 10 hours? Well, I'm going to just plug in 10 for t, because the rate of growth is 40% per hour. And since t is going to be 10 hours, we're in the same units of measurement. So 500 times e raised to the 0.40 times 10 is going to be approximately 27,300. In part C, when will the bacteria reach 80,000? That means solve for t when you know the final amount is 80,000. So 80,000 is going to equal 500 e to the 0.40 t. Since that's an exponential equation, in order to solve it, we're going to have to put it in log form. But before I can put it in log form, I need to divide by 500, and 80,000 divided by 500 is 160. In log form, you're going to take the natural log of the other side. And then we're going to do natural log of 160 divided by 0.40. And t is going to be approximately 12.68. And it's going to be in hours. Example 4. In 2000, the population of the world was 6.1 billion, and the relative rate of growth was 1.4% per year. It is claimed that a rate of 1% per year would make a significant difference in the total population in just a few decades. Test this claim by estimating the population of the world in the year 2050 using a relative rate of growth of A, 1.4% per year, and B, 1% per year. It doesn't seem like there's a significant difference between 1% and 1.4%, but when you're talking about billions of people, we're going to look at exactly what that significant difference is. So let's start with 1.4%. So the initial population is 6.1, and that's in 2000. E to the 0.014 times, well, if my initial population is in 2000 and I want to find the world population in 2050, the time is going to be 50 years. When I plug that into the calculator, I'm going to get approximately 12.3, and that's 12.3 billion. Now I'm going to do it again, except I'm going to do it for 1%. So n of t is equal to 6.1 e to the 0.01 times 50. And this time I'm going to get 10.1, and it's in billions. So the difference here, so 12.3 billion is going to be 12.3 times 1 billion. So let's see, 3, 1, 2, 3, 4, 5, 6, 7, 8. That should be 12.3 billion. 10.1 billion is this. And we're going to see that the difference is actually going to be 2.2 billion. So just that small change in the percent rate of growth could mean the difference of 2.2 billion people in the world. Example 4. A culture starts with 10,000 bacteria and the number doubles every 40 minutes. Find a function n of t is equal to n naught times 2 raised to the t over a that models the number of bacteria after t minutes. So n of t is equal to 10,000 times 2 raised to the t over 40. In part B, instead of writing a doubling time equation, we want to write an equation whose base is e. I'm going to show you 2 different ways of going about writing this equation. So in part B, find a function n of t is equal to n naught e raised to the rt that models the number of bacteria after t minutes. I'm going to show you 2 different ways of doing this. So one way of doing this is because we know the doubling time. If I started with 10,000 bacteria, when I double it, I'm going to have 20,000. E to the r times 40 because it doubles every 40 minutes. So we're going to first divide by 10,000. So I'm going to get 2 is equal to e raised to the 40r. And then to solve this, we're going to put in log form. So it's going to be the natural log of 2 is equal to 40r. And so we're going to do the natural log of 2 divided by 40, which is going to be approximately 0.0173. So the equation is n of t is equal to 10,000 e to the 0.0173 t, where t has to be in minutes because that's what the problem called for. All right, there's another way of doing this, and the other way of doing this has to do with the fact that we know that e and ln cancel each other. So what we're going to do is we're going to rewrite the original equation from part A as an equivalent equation. The equivalent equation is going to be 10,000, and I'm going to rewrite 2 as e to the natural log of 2. And the reason that I can do that is since e and ln cancel each other, I'm really left with just 2 in the parentheses. Except I'm going to leave e raised to the natural log of 2 there, and I'm going to take the natural log of 2, and I'm going to multiply it by t over 1, or t over 40. That's, in essence, I'm going to multiply the natural log of 2 times 1 over 40. And I'm going to get e to the 0.0173 t. So either way I attack this problem, I come up with the same equation. The last type of equation we're going to talk about in part 1 is radioactive decay. We've been spending a lot of time talking about growth, so now we're going to talk a little bit about decay. What I want you to notice about these 2 equations, other than the fact that I switched the variables from n to m, is that the rates are negative. When the rates are positive, it's growth, and when the rates are negative, it's decay. With radioactive decay, we're usually talking about something called a half-life, so rather than doubling. So one way of writing radioactive decay is m of t is equal to m naught times 2 raised to the negative t over h, where h is the half-life. Or if we want to write it in base e, it's going to be m of t is equal to m naught e raised to the negative rt. M naught's going to be your initial mass of the radioactive substance. H is your half-life. The rate r has a little formula. You can find the rate by doing the natural log of 2 divided by the half-life. So in our last example here, number 6, polonium-210 has a half-life of 140 days. Suppose a sample of this substance has a mass of 300 milligrams. Find a function m of t equals m naught times 2 raised to the negative t over h that models the mass remaining after t days. So the equation is going to be m of t is equal to 300 times 2 raised to the negative t over 140. Then in part B, let's move this up, we want to find a function in base e. So find a function m of t equals m naught e raised to the negative rt that models the mass remaining after t days. Well, we said that the rate is the natural log of 2 divided by the half-life. So it's the natural log of 2 divided by 140. So the rate is going to be approximately 0.00495. So now I'm ready to plug it into this equation. M of t is going to equal 300 e raised to the negative 0.00495 t. In part C, it says find the mass remaining after only 1 year. Since t is in days, we're not going to plug in 1 for the year, we're going to plug in 365. So 300e to the negative 0.00495 times 365 is going to be approximately 49.256. And then what was the unit? Milligrams? Milligrams. And then in part D it says, how long will it take for the sample to decay to a mass of 200 milligrams? So when is 200 equal to 300 e to the negative 0.00495 t? So it's an exponential equation. The first thing I have to do is I have to divide by 300. So I'm going to get 2/3 is equal to negative e to the negative 0.00495 t. Now I can put it in log form. So the natural log of 2/3 is going to equal negative 0.00495 t. And I'm going to divide the natural log of 2/3 by negative 0.00495. And I'm going to get approximately 81.9. And the unit of measurement is in days. And that is part 1 of modeling with exponential and logarithmic functions.